Marshal Shepherd and I met in November 2016, just days before the GOESR launch. Marshal wasn't aware that I had developed a graduate certification program for training meteorologists at his alma mater, Florida State, and had recommended his doctoral advisor Henry Fuelberg to head the program. Henry Fuelberg arrived at Florida State just after Paul Dirac had passed away after teaching there from 1971 to 1984. This is the view of Marshal Shepherd expressed in his presentation of 2018.
Consider this. Bank of America building there in Atlanta. You never hear anyone say, "Do you believe if you go to the top of that building and throw a ball off, it's going to fall?" You never hear that because gravity is a thing.
Our team had already visited with physicists at the National High-Field Mag Lab, and we had received a testimonial from the director Cheryl Zavian by the time of our meeting with Marshal Shepherd, who is not trained in electromagnetics and would benefit from the training offered by the graduate certification program. The work of Paul Dirac and Richard Feynman was discussed with the physicists at the Mag Lab, who have a very different worldview than the classical view of the meteorologist. The Pocono Conference of March 30 to April 2, 1948 was the second of three post-war conferences held to discuss quantum physics, arranged by Robert Oppenheimer for the National Academy of Sciences. Held at the Pocono Manor Inn in the Pocono Mountains of Pennsylvania, 28 physicists attended. New participants were Paul Dirac and Richard Feynman. Julian Schwinger gave a day-long presentation of his developments in quantum electrodynamics, QED, the last great fling of the old way of doing quantum mechanics. Richard Feynman offered his version of quantum electrodynamics, introducing Feynman diagrams for the first time. It was unfamiliar and no one followed it, so Feynman was motivated to go back to Cornell and write his work up for publication so others could see it in print. The view of the laws of gravity presented by these scientists is very different from that of Sir Isaac Newton, and that of the meteorologist. Marshal Shepherd would have us believe that the laws of gravity are settled and there is no more debate. But that isn't how science works. The dispute isn't that there is a thing called gravity, it is whether we understand gravity well enough to express it in the language of science, mathematics. And that is where there are very different worldviews between the classical model and the modern model of science as described by Don Lincoln of Fermilabs.
One of the things I like about particle physics is its ability to describe the behavior of matter under every experimental condition we've ever investigated. We call our very successful theory the standard model of particle physics. I made another video that describes this incredible theory. While the standard model covers most of the known fundamental forces, specifically electromagnetism, the strong and weak nuclear forces, and the Higgs field, this model says absolutely nothing about the force that literally binds the universe together, the force of gravity. The reason for this is simple. Gravity is incredibly, ridiculously weaker than the other known forces. On the size of, say, about the size of the atomic nucleus, the other forces all have kind of sort of the same strength, with the weak force being about 100,000 times weaker than the strong force. Now that last statement probably sounds kind of silly because 100,000 sounds like a big difference, like comparing something 4 inches tall to Mount Everest. But gravity is unfathomably weaker still. It is about, wait for it, 100,000 trillion times weaker than the strong force. That's like comparing the tiny proton to the size of the visible universe. It's a huge difference. Since gravity is so weak in the quantum world, there is no chance that we'll ever see any effect due to gravity in a particle physics experiment. In fact, if all we had to go on was the data from particle physics experiments, we wouldn't even know gravity existed. The reason that we know of gravity is because it has an infinite range and up to size scales of the Milky Way or even clusters of galaxies that we can see it works basically like Isaac Newton predicted 350 years ago. It takes the mass of asteroids or planets or stars to see gravity at all. But I don't want to talk about the gravity of the big, which is the domain of astronomy or cosmology, but rather I want to talk about the nature of gravity in the realm of the very small. But I just told you that at sizes comparable to that of a proton, gravity is very weak. So what the heck am I talking about? Well, gravity, even if weak, must apply in the microworld. Now, that's not a very profound thought, but it's true. And since our best theory of gravity is Einstein's theory of general relativity, the most obvious thing to do is just apply that theory to the subatomic realm. As an illustrative example, let's imagine an electron orbiting a nucleus. If you do that, you find that Einstein's theory predicts that the electron would lose energy by the emission of gravity waves and then spiral down into the proton. A similar prediction using classical electromagnetism led to the invention of familiar, or at least well-known, quantum mechanics. This same chain of reasoning suggests that gravity must also have some kind of quantum nature. Ultimately, Einstein's theory of general relativity is a sophisticated theory of gravity, which has taught us that what we experience as gravity is really the bending of space and time. Pretty weird stuff, to be sure, but it's been proven time and again with detailed predictions about the orbit of Mercury and the recent observation of gravitational waves. There's no credible doubt in the scientific community about general relativity. It's a good representation of reality. The problem comes when Einstein's ideas meet quantum mechanics. Now, there's no issue with special relativity. Special relativity and quantum mechanics merge just fine. The result is quantum electrodynamics, quantum chromodynamics, and quantum field theories in general. I made perhaps a dozen videos on those subjects. However, when general relativity, which is to say Einstein's theory of gravity, meets quantum mechanics, the result is very different. The two theories simply can't coexist. You get infinities and conceptual difficulties everywhere. And even though some of the very smartest minds of the last century have worked on this, it's still a problem. We don't know how to merge quantum mechanics and gravity. Another reason to suspect that gravity must have a quantum nature is because A, we definitely have a quantum theory for the other forces, and B, general relativity is a classical theory. It is impossible to seamlessly wed a quantum and classical theory, and this is taken as additional evidence that there should exist a theory of quantum gravity. Otherwise, we'll not be able to write a theory that accurately describes everything in the world of the very small. So, if we accept the idea of quantum gravity, what do we know? Well, there are some basic conclusions we can make that are true for all such theories. One such conclusion is that there should be a particle called a graviton. In just the same way that a quantum theory of electromagnetism predicts that a photon exists, quantum gravity predicts that a graviton should exist. Now, we've never seen a graviton, which means that you shouldn't believe in it. But if it exists, in order to agree with both Newton's and Einstein's theory of gravity, the particle must have certain properties. To have gravity's infinite range, the graviton must be massless. To be only an attractive force, the graviton must have a quantum mechanical spin of 2, which is different from the electron's spin of 1/2 and the photon's spin of 1. The graviton must also be electrically neutral. So this all seems pretty simple. The theory predicts a particle with very specific properties. So it would seem that the next step would be to go out and find it. I mean, my colleagues and I do that sort of thing all the time, right? Of course, the problem is that gravity is so weak. And because it's weak, it's essentially impossible to make a graviton in a particle physics experiment. To all intents and purposes, there is no chance that we'll ever find a graviton, even using the accelerators we might imagine building with the technology of 100 years from now. There is one small possibility we might see a graviton someday soon, but that's only if the universe is much different than it appears. If the universe has additional tiny dimensions beyond the familiar 3, it's possible that we might find gravitons, and even possibly find massive gravitons as well. But this possibility is dependent on these small extra dimensions existing. Frankly, while it's possible, it's a long shot. If you're interested, take a look at my video on the idea. So, getting back to the more basic idea of quantum gravity, Has there been any theoretical progress on the subject? Well, yes and no. There have been a couple of quantum gravity theories proposed that are kind of successful. And by successful, I mean that they're still possible. One is superstring theory, which says that the very smallest building blocks of matter are actually very tiny strings. This theory has been very popular for many years, although some have criticized it for not making testable predictions. If you're interested in the idea, check out my video on the topic. So I hope that this conversation gives you a sense of the complexities involved in a quantum theory of gravity. Realistically, solving this problem will take a long time, but it's a fascinating topic and one that we'll need to solve before we finally have a theory of everything.
For the past 30 years I have presented the weaknesses of linear models including Navier-Stokes equations from Sydney, Australia to Munich, Germany. Ironically, meteorologists admit the limitations of the fluid dynamic equations knowing that the equations break down under conditions outside a few special cases. Based on Newton's laws of motion and gravity, the limitations of which were discussed in detail earlier, it is the linearity and first-order derivations resulting from the study of the actions of the simple harmonic oscillator known as the pendulum that impose the restrictions. These laws are the exception and not the rule against the hopes and aspirations of Sir Isaac Newton. If you Google Richard Carlisle and deterministic chaos, you find a paper published 22 years ago describing these exact events. The linearity of the simple linear harmonic oscillator cannot be cajoled, coerced, noodled, nudged, or fudged into nonlinear behavior. A system as simple as having two components, a single degree of freedom, can exhibit complex behavior beyond the limitations of first-order simple harmonic derivations. It is not the complexity of the system, it is the lack of sophistication of the model. Yet the complex actions of this simple system can accurately be described mathematically using the sophistication of fourth-order derivations of the Dirac equation, the Runge-Kutta fourth-order adaptive polynomials, which were applied to mesoscale convective systems in 2007, a decade after the deterministic chaos paper was published and presented at an international symposium in Anaheim, California in 1997. By waiting for system energy to dissipate, dynamics of the system can return to the linear regime once again where Navier-Stokes are appropriate, as shown by the linear behavior of the double pendulum when at low levels of energy behaves like the simple harmonic oscillator. Once again linearity is restored, but my interest is not within the realm of these low-energy systems but rather in the complex high-energy realm of severe weather conditions that defy description by the archaic models of the current meteorological domain. Navier-Stokes equations of fluid dynamics are known to require linearity between the variables of interest, and it is at high energy, in the petajoule domain, that the chemistry of the atmosphere is altered beyond being modeled by linear methods. The scientific community at large, not only climate science, while giving lip service to chaotic pattern formation as a real phenomenon, generally shrinks back from serious engagement with it, back into the comfortable regions of tidy linear and equilibrium equations. However, there does exist a well-established science of physical and mathematical study of chaotic, nonlinear systems, in which a wide range of nonlinear pattern-forming systems are well understood and characterized. But owing to the human tendency to associate in closed communities, nowhere more in evidence than in the multifaceted scientific world, there is in my view too little engagement between the chaos and nonlinear dynamics experts and scientists in a wide range of natural sciences whose studied systems are, unknown to both sides, accurately and usefully characterized by well-researched nonlinear pattern systems such as the well-known experimental nonlinear oscillator. Plasma cannot be treated like hot gas and is considered a non-Newtonian fluid requiring such nonlinear treatment for which Navier-Stokes doesn't apply. The solution to this dilemma has been known, and rejected by meteorology for over a century. The magnetohydrodynamic theory, for which the Nobel Prize was awarded in 1970. Theoretical development regarding vortex dynamics within atmospheric turbulence has been one of the most challenging scientific problems over the last century. Given the breadth of application, it is clear why there is such an interest in the subject. However, while incremental advances have been made in recent years, with the help of exponentially improving computational resources, there has not been a clear paradigm shift in some time. Even so, there is a slowly growing body of literature utilizing the potentially synergistic relationship between the fields of electromagnetism, M, and hydrodynamics, HD. This synergy is based on the similarity between the equations that govern fluid dynamics and the equations that govern electromagnetism. Thomson, 1931, was one of the first to employ this type of analogous thinking when developing a visual framework for electromagnetism. A table of analogous variables has been compiled from several sources in the figure above. Exploring and exploiting this analogous relationship may be a catalyst for a radical shift in how coherent structure in fluids is studied.